right, let's get started. So we started with the definition for average acceleration. Average acceleration is the change in velocity with respect to time, or rate of change of velocity. So if velocity is subject to change, there will be acceleration produced. That acceleration is defined as average acceleration, and the definition for average acceleration is delta v over delta t, where delta v is the big change in velocity, large change in velocity, and delta t is the total interval over which the change has taken place. But this is in case when the velocity is changing, and velocity can change three ways. It can change its magnitude, it can change its direction, or it can change both magnitude and the direction. Velocity, if moving in a straight line, velocity could be treated as the speed when it comes to its magnitude. So the magnitude of the velocity is speed value if the object is moving in a straight line. Now the same way we did the instantaneous velocity, we also define the instantaneous acceleration. If we want to know acceleration at a certain instant, at a certain time value, this one goes to a very small value, limit delta t approaches to 0, and this becomes A instantaneous. This would give you the value of the acceleration at some instant. Very small value over change in velocity. Okay, sorry, not here, just this. If delta t approaches to 0, delta t is very small, delta v would be very small too. This reaches to one single value for acceleration, which is defined as instantaneous acceleration. So if the acceleration is plotted with respect to time, then in that case, if we have A on vertical axis, T on horizontal axis, as the time has passed, acceleration has changed, that means it's constantly varying. It's a variable acceleration. In order to get the instantaneous value, you will have to find out all these values. But on average, this is going to be somewhere okay, when you average out all the value for the acceleration. Now this average value of acceleration could be a constant acceleration. It could have a positive value, it can have a negative value, it can have a 0 value too if it has averaged out with a positive and negative value. What we do for the acceleration as a constant value, if the acceleration, as you see in the first figure, the acceleration is average acceleration. Acceleration is constantly changing. It increases, it decreases, it becomes negative, it's changing continuously. So when it goes up and down, the average acceleration is somewhere in the middle, is about 1.7 meter per second square. So that over the short interval, we can take the average acceleration as a constant value. We can do the same for the other plot. The acceleration is changing from 3 minus 2 varies up and down, but the average acceleration can be calculated over short time interval. But over the large interval, if the acceleration has been changing a lot, then it is not possible to treat it as a constant value. Then we will have to apply the change in acceleration with respect to time, or integrate it. Use calculus in order to find out. Now, our equation of motions are defined for the situation when the acceleration is constant. If the acceleration is constant, or it that can be treated as a constant value. Acceleration is rarely constant in real life. Most of the time there will be some value linked with the acceleration. However, on average over the short time interval, we can treat it as a constant acceleration. If the acceleration is constant, we can have some equations of motions. I usually take them as 3 equations, but in your book they have taken them as 4 equations. I would just follow your book. The first equation, we are already familiar with, and basically we are going to restate the same definition that we already know for the velocity. We know that V average is equal to xf minus x naught over delta t. What is xf? So here are some terminologies. Delta t, tf minus t naught, change in time. We can take as t naught 0. So we can take this tf is equal to t. So that would take this from our time, we can take this delta t away. All right? So by taking initial time as 0, reference time as 0, and our final time is the total elapsed time, we can get rid of this delta. Is this definition new? No. Where have you seen it before? When? What is it? It's velocity. It's a definition of velocity. It's just being defined in a different way, like as the equation of kinematics, equation of motion. We can also rearrange that equation, xf minus x naught equal to v average t. We can also write it as xf x naught plus v average t. Since there is this xf, I'm also going to replace the xf by just x, and the equation would be x naught minus v average t. It's a more common notation. Nothing right or wrong here, it's just more common notation. Taking x as a final position, taking x naught as the initial position, v average is the average velocity, t is the time elapsed. Okay, remember it's the time elapsed. It's still the same. It's a time interval. However, we have set our initial reference at 0. That is the initial position. What does that equation mean physically? What does it tell you physically? The very last one. X is equal to x naught plus Vt. What is the physical meaning? What do I mean by that when I say the word physical meaning? What am I looking for? words? Does it give you final position? If you know the rate at which the object is moving, if you know the object is moving at a certain value of velocity, and you know the time, and you know the initial position, you can get the final position. If I plot displacement versus time, how this graph is going to look like. For example, if the object is at position x naught, where should I start my graph or line? From here? Yes? From origin? Just like that? Is that correct? For this situation? What does this mean? What is x naught when t is 0? And what is that when t is 0? 0. This graph shows when t is 0, x is 0. Is that correct for our equation? Correct? Really? If I put 0 here, x is equal to x naught. It's not 0, right? So this equation, it does not apply to this. It starts somewhere here at a distance x, initial position. If there is some initial position, if there is no initial position, if it is 0, then you can start from origin. If we find the slope of the graph, delta x over delta t, what would be that? Velocity. The physical meaning of the slope of the graph, displacement versus time. It represents velocity in meter per second or whatever unit you are using. If displacement is taken in meter, thus you will have meter, and if time scale is on second, which it should be. Slope, you started from here. You want to know how much distance it has traveled from here to here. You can add them together. Where was this object initially? X naught. Now it is moving at the rate of v naught, v average. Total time taken for this motion, that will give you the total change in displacement. So this equation, physical meaning is what? You want to know how much distance the object has traveled when it is moving, when it has started its motion from x naught and it has moved through some distance in time interval t. You have to multiply the rate at which it's moving by its time. This will give you total distance it has traveled in time t. Correct? This will give you, v average t will give you the total distance traveled in time t. You add it to the previous distance, that gives you the total distance. So that is the physical understanding of this equation. So these equations, they do mean something. They look like this for a reason. You are calculating the distance or the total displacement produced. This is the first equation of motion for a constant acceleration. Second equation, it comes from the definition of acceleration. Do we know about this equation already? This one does have different quantities in it. You see velocity in there. Definition for acceleration, Vf minus V naught over delta t. If we do the same thing for time interval, taking the initial time as 0, we can write it as V naught over t, right? If I multiply both sides by time, V naught. If I add V naught on both sides, that is our equation of motion, which can be used in a different form, but it is essentially the definition of acceleration that we have done before. Nothing new about it. If A is constant, because this equation is only applicable if acceleration is constant. Otherwise, if it is not constant, then you will have to get its value, change, integrated over the interval, use some calculus. So since it is constant, we can also write it as V is equal to V naught initial velocity plus A t. Remember, this is initial velocity. This is final velocity. This is acceleration. This is the time elapsed. Acceleration must be constant. Okay, you cannot apply this equation this way, okay, if the acceleration is variable or changing. So, and then there are some additional points explaining the same equation. If initial velocity is 0, that means object started from rest. Okay, it was at rest and it started to move. If it is 0, that means final velocity should just be rate multiplied by the total time taken. If the object is decelerating, that means this will be negative. If this is negative, the final velocity would be less than initial velocity, and that's what we expect too, because it is decelerating. If it is accelerating, then the final velocity would be greater than initial velocity. This is entirely new equation. Okay, this is derived from these equations. If A is constant, this should be true as well. That means the average of final velocity and initial velocity should be equal to the average velocity only if the acceleration is constant. That means it's every time it's changing by a same rate. By using this value in this equation, V average becomes V naught plus A T plus V naught divided by 2. So let's call this equation as 1, 2, using 2 in 1. Okay, you plugged in V, replace V by V naught plus AT. These two are the same, they add up. This is left there divided by 2. Now dividing 2 with both of them, V naught plus half AT V average. Let's call this equation as 3. Now using V average in this equation, x naught plus V naught plus half AT multiplied by T. Good? So we used two equations. Get V average in terms of V naught and AT. Plugging it back in the displacement equation, we will get, this T gets multiplied with both x naught, V naught, T plus half AT square. That's our third equation of motion. That is a long one, hard to memorize, but this one is very, very useful when it comes to finding the time related and displacement related problems. Okay, so that is going to be a very challenging part of this course, figuring out which equation you can use in order to find the missing physical quantities. So this equation relates displacement, as you can see, x and x naught. X naught is initial position. All right. What is V naught? Do we know? Initial velocity, T, time passed, A, acceleration, T again, the time passed. What is this X? Final position. What if the motion is vertical? How will equation change? Can someone make a good guess? Yeah. That's vertical motion. It's in the straight line. There will be elapsed time. Yes. Right now, X means it's what? Horizontal. Right? What if it's vertical? Should I make any changes or should I just use X? Why? Who said that? This one is in one dimension, correct? Agree? You don't see any Y in there, you don't see any Z in there, it's only in one dimension. What if it's only vertical? Then you can apply the same equation. However, instead of using X, you can use Y's. Okay? There is a reason I introduced it. Because when we have a free fall, there is acceleration. When I dropped the chalk, it was not a normal acceleration, it was a free fall due to gravity. So the velocity is increasing, but you, instead of x, you take vertical. It doesn't make any difference to the physics of the problem. Okay, it's just the symbols would be different. When you take horizontal motion, you take x. When you take vertical motion, you take y's. The very last equation, I'm not going to derive it. Okay, okay, we will get back to this problem. The very last equation, I will not derive it. I know some students like derivations, some hate it. So I did some for the ones who like it, and I'm not going to do this one for the ones who hate it. So 2a, so this is also one-dimensional horizontal motion. V square, let's just understand the result. X minus x naught. This equation says if there is a constant acceleration again, and then there is a displacement produced, you can find the final velocity. This shows the final velocity after time t. Again, initial velocity, acceleration, and this is the displacement. What if the acceleration is 0? Does that make sense? If acceleration is 0, what does that mean? That means velocity did not change, right? That's what it means. So final velocity should be equal to initial velocity. That is consistent with what we know about the acceleration. If there is no acceleration, velocity should not change. It's constant. When velocity is constant, there is no acceleration anyway. So this one you will use when you will have some unknowns. This is mainly for displacement and accelerations given to you. Then you can work for the velocities, okay? Let's rewrite all the equations, including this one, okay? Because we are going to look at a problem and use one of these equations. Which one was the first one? X is equal to x naught plus v t v is equal to v naught plus a t, where a average, you can put a average there or you can just leave a. X is equal to x naught plus v naught t plus half at square. The very last one, v square v naught square plus 2a delta x. You might notice I replaced x minus x naught by delta x. And it doesn't make any difference. You can write it as x minus delta x. Delta x shows displacement. Displacement is equal to delta x, x minus x naught. So these four equations, they would be key for solving all the problems with constant acceleration. Okay, you cannot apply them if the acceleration is changing. Now let's go back to this problem. How long does it take a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at a constant 2 meters per second square? What information is given? Let's go through it together. So what is the given information to you? So it's like you saw the red signal, you stop, right, at the intersection. Here, you stopped. The car with 2 tires, 2 are hiding. So you start from here, you have what given? You do know the distance. So what's the initial position? 0. What's the final position? 30. Very good. Right? And you know the acceleration, which is 2.00 meter per second square. You have to go up to at least 3 significant figures. What else? What is it? 0. This is also given because it starts from rest. What are we looking for? Oh, the time. Okay. What do we need to find? The total time it takes to cross the intersection. Which equation is possible to use based on what's given? Can we use the very first one? No, we don't have the averaged velocity. Can we use the second one? We don't have the final velocity. Can we use the very last one? The very last one. Yes? There is no t in it. It doesn't have any t involved in it. There is no time. This one has time in it. Can we use it? Try it. Plug everything in, see what you get. Does it give you a quadratic equation? Yes? No? I don't think so, because V naught sets this equation, this part 0. So that goes away. right? You just take the square root of 30 and you will have the answer. Very simple calculation. I'm going to give you the same problem with some addition to it. If this initial speed is not 0, okay, I'm going to change some numbers here. So the acceleration is different. This is 10 meter per second. So this car is not at rest. It is already moving, and it is going to go through a distance of 100 meter, and the acceleration, let's keep it the same. You still want to know the time. Okay, work on it at home. Okay, come back with some answers. See how this problem is different from the one you have done before. You have everything given, but the only difference is this time it doesn't start from the rest. There will be initial speed. You will end up having a quadratic equation there. Okay, you will have to apply the quadratic formula in order to get the two values for time. Okay, I will be looking for answers. If I forget, then who is going to remind me? No one. There are plenty of questions, but we will come back when we have time, but I'm going to start with free fall. When we are talking about the object moving under a constant acceleration, that is the acceleration due to gravity, thrown object, drop object, when they move vertically under the effect of gravity or Earth's pull, that our acceleration would always be 9.8 meter per second square. It simply means wherever the object is, if it has started from some position, it will only accelerate at a rate of 9.8 meter per second square. Okay, for dropped object, the initial speed is what? When you drop something, would there be any initial speed? No, it's 0 because it's being dropped. You're not forcing it down. You are not applying any force on it. For thrown object, up or down, V naught is not equal to 0 because you are throwing them. You have to give them some initial speed vertically or horizontally in order for it to move. The same equations can be rewritten in the form of the acceleration. Acceleration due to gravity is constant value. We can rewrite the same equations that we have before in G form. Now you may notice I put a negative there. Everything which is downward, we are going to take as negative G. So A is equal to negative G, negative 9.8 meter per second square. However, when you have already put negative there, then do not plug in negative 9.8. Then it would be wrong. Okay? Because we have already taken care of its downward motion in the equation. Y is equal to Y naught plus V naught t minus half GT square. Final equation V square, V naught square minus 2G delta Y. So when we will deal with some problems where the acceleration is constant, but that constant acceleration is due to gravity. That means you are talking about the falling object or the object in the free fall. In that case, you will have to use one of these equations. You do need to put the negative sign with g, but when you plug in g, you will put just 9.8 meter per second square. Just write it down and we will work on it in next class. Just omit the first line. The figure shows the position of the ball. I don't have the figure, but I can draw the figure to go with it. So there is a ball which has been thrown downward with 4.9 meter per second, and the height of the building is given. You want to know how much time it will take to reach the ground and what is the velocity when it arrives the ground. We'll start from here.